All right, so yeah, if we look at this case here, this is a nice one because this looks at multiple levels. We're going from bismuth to polonium to lead. Bismuth beta decays, and so goes from 83 to 84. So that would be, it's gaining a proton, therefore it shoots out an electron. So that'd be beta minus decay. And then it alpha decays from polonium to lead, and we can see that here, and that drops down. So therefore, this alpha particle that shoots out, and I should draw just probably a straight line, right? Because this is a particle, two protons, two neutrons that shoots out with 7.6 mega electron volts of energy as it shoots out. And yeah, and then we have lead, which is very stable. So here's what we're talking about with the decay series. Here we have a very heavy nucleus, a 232 nucleus here with 90 protons, and this is thorium. And then what happens is thorium has, a very large nucleus, and it will alpha decay. And as it alpha decays, it goes from 232 to 228. So, and then it also loses 2 protons, so it goes from 90 to 88. But then what will happen? Well, the nucleus itself here will go from 88, which I don't have that listed here. It's a different element. And then it'll beta decay and then beta decay again. And so therefore, let me do that in another color. It's going to beta decay here and then beta decay here. So 88 to 89, so that's gaining a proton, so that's beta minus decay. So you have beta minus decay, then beta minus decay. And then at that point, it will alpha decay again. And after it alpha decays, we go to another alpha decay, and then it'll shoot out another one, and then another alpha decay, and then another alpha decay, and then beta minus, and then, or maybe it'll do an alpha decay prior to that. And so you have these series which, you see the elements do this over and over and over again, and you can see the pattern with these different elements. And they'll have these different series where, you have the different expectations, because that nucleus either, will naturally do that next decay. So the law of radioactive decay looks like this. We start with 100,000 atoms, and let's say we have a half-life of 1 year. After 1 year, half of those particles will decay. So, if we had 100,000 atoms, after a year, half of those, and if the half-life is 1 year, half of those are decayed. So half of those are a new element, and then in white here I have this as the original element. So half are like that. So with 10,000 atoms over a year, 5,000 would be the original, and then 5,000 would be also, or would be that new element that it decayed into. So again, over that year, only 5,000 decays versus 50,000 decays with this. And so if we start with more atoms, we're going to get more decays, and that should make sense. And so the number of nuclei that will decay per second is proportional to how many atoms that are present. If you have more atoms, you're going to have more decays, per second. And so, and we can't know when a particular nucleus will decay, but statistically we can determine the likelihood of decay over time. So again, if we have more atoms, we're going to have more decays, and as we can see in this example. So if we look at these graphs, this is very helpful for us here. This is nuclei in a period of time. And so, we're starting here with 200 nuclei, and, based on this graph, and this is time in seconds, we could find things like half-life. And so if we look at that, we say, okay, if we start with 200 nuclei, how long does it take to where we only have 100 of the original, and then we have, 100 of the new? And then maybe those are decaying too, but we still have 100 of the original. Well, we come here and we say, okay, after 5 seconds, we still have 100. So that's the half-life. The half-life of this element would be 5 seconds. And then if we look at the second graph, this is the original nuclei over time, And then Y is representing the number of daughter nuclei, right? So you're starting with 0 daughter nuclei, and then over time, at 5 seconds, you have half of the original, half of the daughter nuclei, and then over time, the daughter nuclei are more and more and more, and then the original is less and less and less. And so yeah, so and define the half-life of the substance is what you do. So how long does it take to get half of the original? And then how much is left after 3 half-lives? Why don't you go ahead and do that? Go ahead and pause the clip and write that down, and then you can we'll talk about that. All right, so after 1 half-life, 5 seconds, we have 100. After 10 seconds, we have half of that, which is 50. And then after another half-life, we have 25 that are left of the original. So this simulation from PhET does a really good job kind of giving you a good picture of half-life. And so I show this in class. I encourage you to look up, PhET and then type in radioactive dating game. And there's some pretty good stuff in there looking at just giving you a visual for half-life and being able to see that, especially for, elements that take a long time to decay. All right, so barium has a half-life of 10.6 minutes. If there was originally 600 grams of barium, how much is left after 53 minutes, just using logic? And so, yeah, based on what we've seen so far, go ahead and pause the clip and see if you can figure this out. How much would be left after 53 minutes? I'll give you a hint. It's gonna work out very evenly there with 10.6 minutes. Go ahead and think through that and pause the clip and work through that, and we'll see how you do. Okay, so 53 minutes, 10.6 minutes. It's going to be 5 half-lives. Therefore, if we start with 600 grams, after 1 half-life, we'll be left with 300 grams. After the next half-life, will be half of that, so 150 grams. After another half-life, half of that, 75 grams. After the 4th half-life, 37.5 grams. And after the 5th half-life, 18.75 grams. So after 53 minutes, all you're left with is 18.75 grams of barium. The original amount was 600, and so you're going to go down to, very few of the original. All right, so rate of decay, again, is proportional to the half-life. So radon has a half-life of 55.6 seconds. If radon emits 120 particles every second, how many particles per second will emit after 166.8 seconds? And so, yeah, let's go ahead and use the same kind of logic here. See how you can do here with that. So go ahead and pause the clip and give this a try. When you're ready to check, you can hit play to continue. Okay, so that's going to be 3 half-lives, 166.8 seconds, and so 55.6 seconds is 1 half-life. So it'll be 3 half-lives. So the activity is going to go down to 60 per second after the first half-life, because originally 120 per second. You're going to have 120 second events every second. So then you're going to go down to 60. Another half-life, go down to 30, and then after the 3rd half-life, you're only going to get 15 events per second, because again, as you get smaller and smaller quantities, you're going to have less and less events that can happen. All right, so let's take a look at this value here, the becquerel. And 1 becquerel is equal to 1 decay per second. And this helps us look at activity. So in the last problem, the substance had 120 decays per second, so it would be 120 becquerels. So after 1 half-life, you'd have 60. After 2 half-lives, 30. And after 3 half-lives, 15. All right, so yeah, why don't you go ahead and pause the clip and read through this. This is some interesting history here that is helpful for us as part of the IB curriculum here. So go ahead and pause this and read through, and once you're ready, you can hit play to continue. Okay, so this is H18a, At time equals 0, there are 1.6 times 10 to the 22nd nuclei of thallium. After 3 minutes, there are 0.8 times 10 to the 22nd nuclei left of thallium and 0.8 times 10 to the 22nd nuclei of the decayed substance. If the original activity of the substance was 6 times 10 to the 19th becquerels, what is the activity after 12 minutes? And so with this one, we can, kind of work through that same logic, as we work through that. So let's go ahead and do that. From 1.6 times 10 to the 22nd to 0.8 times 10 to the 22nd is a half-life. So again here, this 1.6 times 10 to the 22nd goes down to this. So that's a half-life, and so therefore, 3 minutes is the half-life for this substance, because we're going from this amount of nuclei to this, which is half, and it takes 3 minutes. So we have the half-life. In 12 minutes, there are 4 half-lives, therefore. So because of that, yeah, we should be able to find the activity. Why don't you go ahead and pause the clip? I probably already gave you too much here, but go ahead and pause the clip and solve through the rest of this and see if you can figure out what's happening here with the activity after 12 minutes, and then hit play when you're ready to continue. Okay, so the original activity was 6 times 10 to the 19th. After the first half-life, half of that. After the second half-life, half of that. After the third half-life, half of that. 0.75 times 10 to the 19th becquerels will be the activity after those half-lives. Oh yeah, and then we have the fourth half-life, half of that, so 0.375 times 10 to the 19th. Okay, so when we talk about the probability of decay, any given nucleus in a sample has a 50% chance of decaying over one half-life. Yeah, and so that should make sense, right? So each nucleus has a certain, we don't know what's going to happen to that. It could wait for a bunch of half-lives, right? But again, you have the probability there where within that half-life, half of those have to decay, so it's got a 50% chance. If it didn't decay in the first one, it has another chance in the second half-life. So if you think about that, you have those, you have the full amount of substance, right? And then after a half-life, half of those are the original, the other half are a new nucleus. And so inside here, you have another half-life, which after that, half of those are going to be the new nucleus. And then again, another after a half-life, half of those, and then half of those, and then half of those, and it gets higher and higher and higher probability that those are going to be gone. And so if you think about it, this is a nice tree diagram. I encourage you to write this out. Yeah, for the first half-life here, we have this nucleus. Let's say it decays, right? It has a 50% chance for it to decay. Now, let's say it didn't decay. Well, it's got another 50% chance. It might decay, it might not, right? So maybe it won't. But again, the probability of decay during the second half-life is higher. And then again, it'll happen again. You have it here, it could not decay, or maybe it will decay. And again, you just have, well, I guess down arrow means decay, and then up arrow it means it will not. And then again, another probability. So if we add up the probabilities, we have 1/2 here, and then we have half of a chance that, again, it'll get to that point. And yeah, so we can do that. So we have the probability of the first one, and then we have the probability of the second one, half of a chance, half a chance. And yeah, so again, 0.75% chance after that one. And so let's go ahead and try this one. What is the probability that an isotope with a half-life of 20 minutes will decay after an hour? And so use that same logic here. Let's see how you can do with that. And so go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. Okay, so for the first half-life, 50% chance. For the second half-life, half of a chance, 0.25. For the third half of a half of a half, 0.125. And then, yeah, so that's 3, right? So an hour, 20 minutes, 20 minutes, 20 minutes. So 87.5% chance that, you know, we'll be able to have that particle decay. So very high probability that that particle will decay after 3 half-lives, but maybe not. Maybe it's within that 12.5% that still hasn't decayed yet. Okay, so forced convection is where you blow air across, and you know, that could be like, you know, pouring milk in a coffee, you blow across the top and you force the convection. Remember the mass movement of molecules from one place to the other, way of heat transfer. Natural convection is where you leave it alone, and so the greater the temperature difference between the outside and inside of the cup, the faster it will cool off, and we see that. So for instance, if you put your coffee in a snowbank, well, yeah, you're going to have a quicker rate of transfer there. So just as in activity, the more atoms you have, the more decays. The greater temperature difference, the faster heat is transferred in convection. So like in that original one that I showed you there with that 100, I think it was 100,000 atoms, which is actually not very many, right? But compared to the 10,000 that I gave you, you're going to have a much higher activity where you have more atoms, right? You have more chances to decay because you just have more atoms there. And so, you know, this kind of analogy can maybe be helpful for you to think between what we just talked about and what we've looked at in the past.